Welcome back to the deep dive. And I have to be honest with you, when I first looked at the stack of research we're covering today, I genuinely thought I'd made a filing error.
It does look like a bit of a scramble when you just glance at the titles.
A scramble is putting it lightly. I mean, we have these heavy-duty papers on, 19th century astronomy and orbital mechanics.
Right.
We have a Reddit thread about vector geometry, a blistering critique of modern economics. And then all of a sudden, we take this hard left turn into psychology guides and a medical ethics paper on past life regression.
It sounds completely disjointed, but the more you read, the more you realize there's a single heavy anchor holding all of this together.
It's one word.
Yep. Regression.
Exactly. And what's so fascinating to me is how that one word dominates two completely conflicting worlds. It's like a linguistic shapeshifter.
That is the hook for me, because
Yeah.
in one pile of our sources, the data side regression is this superpower. It's all about moving forward.
Right, predicting the future. It's how we land rovers on Mars. It's how we figure out car insurance rates. It's a tool for, progress.
But then you cross the border into the other pile, the psychology side, and regression is the exact opposite.
It's about sliding backward.
Reverting to a less developed, more primitive version of yourself.
So our mission today is to map out this territory. We're going to start with the math, the tool that essentially runs the modern world, and why one of our sources argues it's actually junk science when economists try to use it.
That is a spicy take. We'll definitely unpack that one.
Then we're going to look at neural networks, which, spoiler alert, are just regression on steroids.
It's a very complex version of it, yeah.
And finally, we'll end up on the therapist's couch, looking at why stressed out adults throw tantrums and the very weird, very controversial world of past life regression.
It's a journey, I think, from the outer edges of the solar system to the inner workings of the amygdala.
So let's eat the vegetables first. Let's talk about the math. I think for most people, the word regression triggers the sort of fight or flight response from high school calculus. But this goes back way further.
Much further. To really get where this comes from, we have to look at the early 1800s. We're talking about Adrien-Marie Legendre in 1805 and Carl Friedrich Gauss in 1809.
And they weren't trying to pass a test. They were trying to solve a massive high-stakes problem.
They were tracking planets and comets. This was the golden age of astronomy, but they had a problem. They had all these observations.
Data points.
Exactly. Data points of where a comet was in the sky on different nights. But observations, they have errors, telescopes aren't perfect, the atmosphere distorts things.
Human eyes get tired.
Exactly. So they had this scatter of dots on a page, but they needed to know the actual path.
The line through the dots.
Precisely. They needed to draw a line that best fit those dots to predict where the comet would be next week. So they developed the method of least squares.
Okay, let's not get too bogged down in the formula here.
No. Imagine drawing a line through a cloud of dots. You measure the vertical distance from every single dot to your line, square those distances so you don't have negatives, and then you add them all up.
And the goal is to get that total number as small as possible.
That's it. The best line is the one where that total error is the smallest possible value. You're minimizing the error to find the truth that's hidden in all the noise.
And that's the grandfather of all modern regression.
It is. It's asking that fundamental question. If I know input X, can I predict output Y?
Okay, so that's the linear version, a straight line. But our textbook source makes this huge distinction between linear and nonlinear. And this feels crucial because, well, life isn't usually a straight line.
It rarely is. If you try to force a straight line onto a curved reality, your predictions will be absolute garbage. The source uses human growth as a perfect example of this.
Right. If human growth were linear and you grew, say, 2 inches a year, every year from birth,
You'd be a giant by the time you hit retirement. You just keep growing forever.
we'd be dodging 12-foot-tall pensioners at the grocery store.
Which obviously doesn't happen. Growth is nonlinear. You have a rapid spike after birth, another explosion at puberty, and then, and this is key, it plateaus.
It curves flat.
It levels off. And if you used a linear model to predict an adult's height based on their growth rate as a toddler, you'd be wildly, wildly wrong.
The other example I really like was the dose response in medicine. This is that S-curve, right?
Yes, the logistic model.
Yeah.
This is so vital in pharmacology. Imagine you have a headache. You take a tiny crumb of ibuprofen, let's say 1 milligram.
Nothing happens.
Nothing happens. That's the bottom of the S-curve. It's flat. You're in the no-effect zone.
Then you take a normal dose, say 200 milligrams.
And boom, the pain vanishes. The curve just shoots up vertically. That's the steep part of the S. You're getting a massive return on investment.
But then let's say you decide to take 2,000 milligrams.
which you should absolutely not do.
Please do not do that.
But mathematically, the curve flattens out again at the top. You hit saturation. Taking more of the drug doesn't give you more pain relief.
The receptors are just full.
They're full. It just damages your body. A linear model would assume that if 200 milligrams is good, 2,000 milligrams is 10 times better. It wouldn't just be wrong, it would be dangerous.
So the math has to bend to match reality. Now, whether we're drawing lines or curves, there's this one symbol that seems to rule them all. R squared.
Ah, yes. The metric of truth. Or at least the metric of perceived truth.
We found a really interesting explanation for this, of all places, in a Reddit thread. It broke it down better than the textbook, I think. But first, give us the formal definition.
Okay, so technically, R squared represents the percentage of variation in the outcome that is explained by your model.
Okay, let's translate that. If I build a model to predict house prices and my R squared is 0.80, what does that mean?
It means your model understands 80% of what makes house prices change. The square footage, the location, number of bedrooms, your math has captured 80% of the story.
In the other 20%.
That's the noise. That's randomness. Maybe the buyer was in a bad mood, or there was a weird smell in the basement you couldn't measure. 1.0 would be perfect accuracy. 0.0 means your model explains nothing.
Now, the Reddit thread had this geometric way of visualizing it that really clicked for me. It said to imagine two arrows, or vectors, shooting out from the same point.
This is such a great way to think about it. One arrow is reality, the data you actually observed.
And the other arrow is your prediction, what your model said would happen.
And R squared is basically measuring the angle between those two arrows.
It's the cosine, right?
It relates to the cosine of the angle, yeah. If your prediction arrow is pointing in the exact same direction as the reality arrow, the angle is 0. The cosine is 1. Your R squared is 1.
Perfection.
The model and reality are perfectly aligned.
But if they're at a 90-degree angle?
They're perpendicular,
Yeah.
totally unrelated. The cosine is 0. Your model is pointing north, and reality is heading east. You're completely lost.
That makes so much sense. You want the arrows to hug. But, and here's the warning label that was all over our sources. A high R squared isn't always a good thing.
No, this is the classic trap of overfitting. You can artificially force those arrows to touch.
How?
If you make your math complicated enough, if you add enough variables and squiggles to your line, you can build a model that hits every single data point perfectly.
But that's cheating.
It's worse than cheating. It's self-deception. You're not modeling the underlying rule. You're just modeling the noise. You're memorizing the data instead of understanding it.
Like a student who memorizes the answers to the practice test but fails the actual exam.
Exactly. They didn't learn the concepts.
Which brings us perfectly to the biggest skeptic in our stack today, Stephen J. Cleese. He wrote this paper in the Real World Economics Review, and he is essentially yelling from the rooftops that economists are overfitting their way to disaster.
Cleese is not holding back. He calls the use of regression in economics ad hoc empiricism run rampant.
Which is academic speak for you guys are just making this up as you go along.
Pretty much. His whole argument is that regression works for Gauss and his planets because physics is stable. Gravity doesn't have a bad day.
An electron doesn't change its mind.
Right. But in social systems, in economics, the conditions for regression to work are almost never met.
And he focuses on the earnings function. This is that classic equation where they try to predict how much money a person will earn based on things like years of schooling, age.
Right. And Cleese just drops the hammer with something called omitted variable bias.
Okay, explain that for us.
So the math of regression only works if you include every single variable that causes the result. If you leave even one important one out, the whole thing breaks.
So for earnings, you have education, sure, but what about natural intelligence? Or ambition, or just pure luck?
Can you measure ambition on a scale of 1 to 10?
No.
Can you quantify luck?
No.
And because you can't put them in the equation, economists just leave them out.
And Cleese says that ruins everything.
It does. Because maybe the person who went to school for 20 years also just happens to be naturally more ambitious. If you leave ambition out of the model, the math doesn't know where to put that effect.
So it just gives all the credit to the education variable.
Exactly. It inflates the value of education because it's stealing the credit from the invisible variables you couldn't measure.
So we end up with these big policy papers saying education increases income by X%, but it's basically a mirage.
That's his conclusion. He says we're pretending to have physics-level precision in a world that is messy, chaotic, and fundamentally unpredictable. He thinks we need to be a lot more humble.
It's a sobering thought. We love data because it feels safe, but sometimes it's just a sophisticated guess. However, regression didn't stop with economics. It evolved, and this is where we get into the sci-fi stuff.
Neural
I
networks.
think for a lot of people, neural networks, AI, it feels like magic, but our source says, no, it's just regression on steroids.
It really is.
Yeah.
If you strip away all the marketing hype, a neural network is just layers and layers of regression equations, all stacked on top of each other.
But with a twist, right? It's not just input leads to output. There's something in the middle.
The hidden nodes. Imagine a web. You put your inputs in one side, but instead of going straight to the answer, they go into this messy middle layer of nodes. And each node has to make a decision.
The activation function.
Right. And guess what shape that function usually takes?
Don't tell me. It's the S-curve again.
The logistic curve. It's mimicking a biological neuron. The node sits there gathering signal, 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 and nothing happens. It's at the bottom of the S. But once the total signal hits a certain threshold, boom, it fires. It shoots up the curve and passes the message on to the next layer.
That's incredible. So it's using that same nonlinear math from the drug dosage to simulate a thought. But our source on this points out that neural networks are even more prone to that overfitting problem.
Oh, massively. Because they're so complex. A modern AI has billions of parameters. It could so easily just memorize the training data and then fail in the real world.
So how do they stop it?
They use a technique called penalized least squares.
That sounds like a punishment.
Kind of is. They add a penalty for complexity into the math. They basically tell the model, hey, you can fit the data, but if you get too wild, if your equation gets too complicated, I'm going to penalize your score.
It's like putting a leash on the AI.
That's a great way to put it. They call it weight decay. It forces the model to keep things simple, to look for the broad, strong patterns, not the tiny, noisy details.
The source gave a real-world example of this working predicting costs for ischemic heart disease.
This was fascinating. They put a neural network against a standard regression model to predict hospital bills. And the neural network won, specifically because it could handle the weird, nonlinear spikes in cost when a patient needs multiple interventions.
Standard regression was too rigid.
Too rigid. The neural network could bend.
So, regression, when it has hidden nodes and a complexity leash, can predict heart attacks. But now, we have to pivot. We are leaving the data lab, we're leaving the hospital, and we are going inside the mind.
From math to the mechanism of the soul.
We're looking at the attachment project source now, and here regression is not a statistical tool. It is a defense mechanism.
This is a concept with roots in Freud, but the modern science is very biological. Psychological regression is what happens when an adult, under stress, reverts to an earlier stage of development.
Essentially explaining why a 40-year-old might scream and stomp his feet when the Wi-Fi goes out.
Exactly that. But it's not just acting out. The source explains the neurology. It's a battle between the prefrontal cortex and the amygdala.
The CEO and the caveman.
That's a perfect analogy. The prefrontal cortex is the CEO. It handles logic, future planning, emotional regulation. The amygdala is the threat detector. It's ancient and it's reactive.
And everyone has a window of tolerance.
Right. That's your capacity to handle stress. But when the stress becomes too much, when you get flooded, you get pushed out of that window. And when that happens, the CEO goes offline.
The prefrontal cortex literally shuts down.
It does. And the caveman takes the wheel.
And the caveman doesn't know how to negotiate or use I statements.
The caveman knows what worked when you were 3 years old.
The source lists some of these behaviors. Involuntary things, like crying, tantrums, or checking out.
Just staring at a wall. Or even bedwetting in really extreme trauma cases. The brain is just seeking the safety of the past.
What I found really useful was how this ties into attachment styles. Because we don't all regress in the same way.
No, your attachment style dictates the flavor of your regression.
So if I have an anxious attachment style,
You regress by clinging. You might start using baby talk or acting helpless. Subconsciously, you're trying to force your partner into the role of a parent. You want them to fix it.
and if I'm avoidant,
You go the other way. You regress by withdrawing, isolating. You go into a shell, like a child hiding under the bed from a scary noise.
it really reframes arguments, doesn't it? You see a couple fighting, and one is yelling, following the other from room to room. That's the anxious regression.
And the other one is locking the door and refusing to speak.
That's the avoidant regression.
It's just two terrified children in adult bodies, both trying to find safety in completely opposite ways.
And realizing the window of tolerance has been shattered is probably more helpful than trying to win the argument with logic.
You can't use logic when the CEO is offline. You have to restore safety first.
Now, if reverting to childhood is a defense mechanism, our final source asks a very strange question. What if you revert beyond childhood?
And this is the most controversial part of our stack today, past life regression.
We're looking at a paper by Gabriel Andrade from PubMed Central, and this is analyzing the practice of using hypnosis to recover memories of previous lives.
Right. This was popularized by people like Dr. Brian Weiss. The theory is that your current phobia, say of fear of water, is caused by drowning in a past life.
And if you can regress back and remember it, you'll be cured.
That's the premise. But Andrade is, well, let's just say he's not buying it.
He's highly skeptical.
Very. And his main concern is ethical. He argues that this therapy carries a massive risk of creating false memories.
The idea that the therapist isn't uncovering a memory but accidentally planting one?
Exactly. Hypnosis puts the brain in a highly suggestible state. Andrade argues this violates non-malfeasance, the duty to do no harm. If you convince a patient they were murdered in the 1800s and that trauma never actually happened, you're actively damaging their psyche.
He brings up the Bridey Murphy case. I had never heard of this, but it is wild.
It's a classic case. In the 1950s, a woman named Virginia Tighe was hypnotized. She starts speaking in an Irish brogue, claims to be a 19th century woman named Bridey Murphy. She knows all these details about Ireland.
Things she shouldn't know.
Right. It sounded like proof of reincarnation.
Until the journalists started digging.
And it turned out Virginia grew up next door to an Irish immigrant named Bridey Murphy Corwell.
No way.
Yes. Virginia had listened to this woman's stories as a little girl. She had forgotten the source, but the details were all stored in her brain.
So under hypnosis, her brain just remixed those old memories into a new persona.
It's a known phenomenon called cryptomnesia, hidden memory. The brain files off the serial numbers, and you mistake an old memory for a new revelation.
Andrade also goes after Ian Stevenson's research. Stevenson is usually the guy people point to for this scientific proof of reincarnation.
Right, because he interviewed thousands of kids who claimed to remember past lives. But Andrade points out all the holes in that methodology.
Like what?
Well, Stevenson didn't speak the local languages. He used translators who already believed in reincarnation. And crucially, he usually arrived in these villages after the families had already met and swapped stories.
So the data was already contaminated?
Completely contaminated. Andrade's point isn't to mock spirituality. It's to say, extraordinary claims require extraordinary evidence. And there's usually a simpler biological explanation.
Like the Mozart example, people say he must be a reincarnated master to play that well at age 5.
And Andrade says no, he likely just had a genetically freakish auditory cortex. We don't need metaphysics to explain biological genius.
We have covered a lot of ground. From Legendre drawing lines through stars, to neural networks predicting heart attacks, to adults hiding under emotional bed covers. When you look at all this together, what's the thread?
I think whether we're talking about statistics or psychology, regression is really about our relationship with chaos.
How so?
Think about it. In the math world, regression is about finding the pattern in the noise. We look backward at the data, the past, to try and draw a line that makes the future predictable.
We want to feel like we have control.
We want control. We want to know that X leads to Y. And in the psychological world, it's the same desire. When the present becomes too chaotic, too painful, our brains slide backward. We retreat to a time or a behavior that felt safe.
So the statistician draws a line to control the future. The stressed adult throws a tantrum to control the present.
Precisely. It's all a reaction to being overwhelmed.
So for you, listening, what are the big takeaways to put in your pocket?
On the math side, be a skeptic. Remember Cleese.
Yeah.
When you see a model or a statistic, just ask yourself, what variables did they leave out? Are they measuring reality or are they just overfitting the noise?
And on the mind side,
be compassionate. If you see someone or yourself regressing, acting childish, realize it's not a character flaw. It's a signal. The CEO is offline. The window of tolerance is broken.
You don't need to win the debate.
You need to find safety.
I love that. Now, I have one final slightly disturbing thought that's been nagging me since we talked about neural networks.
Lay it on me.
Okay, so we said that under stress, the human brain shuts down its logic centers and reverts to simple emotional behaviors.
Correct.
And we said that our most advanced AI neural networks works by mimicking those same brain structures using regression math.
Yes. I think I see where you're going with this.
So if we keep building AI to be more and more like us, are we eventually going to build computers that have a window of tolerance? Are we going to see a supercomputer get overwhelmed with data and just throw a digital tantrum?
That is a terrifying thought.
Yeah.
Imagine an AI running a power grid that hits its stress limit and just shuts everything down until it gets a virtual comfort blanket.
If my laptop starts asking for a juice box, I am moving to the woods. Thanks for diving deep with us.
Thank you.